we know how to deal with lines in 2 dimensions, but I think it's worth revisiting 2 dimensions with lines by looking at our equation of lines as a vector form. We've talked about parametric equations already, and so when we talk about a line in vector form, it's essentially the same thing as dealing with it in parametric equations. In 3 dimensions, we're also going to be able to express our equation of a line in symmetric equations, they call it. But we're also going to be able to write things in vector and parametric form as well. And then one of the key things to be able to do is to be able to find an equation of a line given 2 points. So we know how to do that using points and slopes and stuff, but we want to do this from a vector perspective so that we can extend this to 3 dimensions. So that's our main focus, and if we get to finding the equation of a plane, that's great. We're going to try to take a look at an equation of a plane from a couple of perspectives as well. So let's take a look at lines. In 2D, we generally can find an equation of a line if we have a point and a slope, right? But a line is defined by 2 points, so if we have 2 points, we can generally find the slope by doing the rise over run thing. And so we got y equals, well, let's call it x1 and y1, and then the slope is b, or m. So y minus y1 is equal to m x minus x1. So that's our usual way of finding the equation of a line. What we're going to do is try to find the equation of a line using vectors instead. And what we can try to understand is the idea that a vector in standard position is something that starts from 0 and points at a point, right? So let's find a specific example. Let's have a couple of points that we're going to try to connect. So let's try to connect, give me a point on the xy plane. 5, 1. And another point, 2, 3. So what we're going to try to do is try to draw a line using vectors. And the way we're going to draw a line using vectors is that we're going to have a vector in standard position that would point to one of those points. And it really doesn't matter which point we point to first, which is going to be, it might be a little bit of an issue because then we can have different answers for our results. And then what we want to do is we want to travel to be able to create, let's see if I can draw this line. Maybe if I can draw the line drawing. Not so thick. I can adjust it. Or maybe I wanted a purple color. So in general, you might want to, so you want to try to get to this line, and you want a vector that would be pointing to this line. So the idea behind this parametric equation, or this vector equation, is to be able to point at every single point on this line to draw it out. So that's our key. And the way we're going to do this is by addition and scalar multiplication. Maybe I should put this in a new page so that I can have a better, more room. So this is my idea, is to be able to point at every single point on that line. And what we can do is we can start with any of these points. Let's start with a point 5, 1. So I can get to this point 5, 1 by this vector right here. I also want to be able to get to the point 2, 3, since that's another point that we have. So 2, 3 is the point on the line. But if we decide that we want another point on the line, let's say there's another point over here, right, between 2, 3, and 5, 1, that we also want to get to. So if all I have are the points 5, 1, and 2, 3, how do you think we can get to this other point over here? Any ideas? Can average the two?
Is halfway?
Yeah, midpoint, or the average of the two would probably work. Let's think of addition. What? Yeah, this was working better in my head earlier. Yeah, that's what I want to do. I want to go from 5, 1 and somehow end up at these points. Yeah, well, let me just tell you. Actually, Frederick has the idea already. But let's see if I could just actually get this going. Where's my, is that the one? So what I'm going to do is I'm going to need help from this vector that finds the difference between the 2 points that were given to me. And if I take that vector, if I find that vector first, let's resolve this vector over here. This vector, I'm going to take a copy of it. And I'm going to call this vector D. And this is a vector. So D, how would you find D? So it's B, subtraction, right? I have two vectors over here, or the points 3, 2, and 5, 1. It's a subtraction. Which one goes first? The 5, 1 or the 2, 3? Head minus tail, right? So it's 2, 3 minus 5, 1. And so this turns out to be -3, 2. So that's my vector -3, 2. And I called it D because it describes the direction of the line. And so now let me ask that question again. How can I get to this vector right here, or to this point? I would go to 5, 1. I'm going to go about it the longer way. I'm going to go to 5, 1, and then I would add half of D. Right? So for now, let's just put 5, 1 plus 1/2 of your D vector. So let's say I wanted to get to this point right here. So I put another D over here to say that this is twice as long as the D. So how can I get to this point right here? Okay, but if I just want to use 5, 1, I'll be 5, 1 plus 5, 1 plus minus 3, 2. But I'm doing twice as long, right? So it'll be twice as long.
Oh, so I couldn't see how long the actual D was because it was being covered by the red.
What's the point on halfway or twice as long?
Say it again?
There's a point that it's not twice as long as perfectly half, and that wouldn't work, right?
Yeah, well, if it's not perfectly half, then we can just put in a third or a fourth or whatever.
Just scale it.
Yeah, so we're just going to scale it.
Okay.
And that's going to be our key. In fact, we can even go back here. I'm out of colors. We can go back here and go on the negative side. I need to find a way to flip this around. I could go on the negative side to get to this point over here by starting with 5, 1 again, and then adding, well, instead of adding some scalar multiple of 3, 2, I would actually subtract and multiply by a negative number. That gives me this point. So that's going to be our key, is that if our line, and I'm going to put another expression over here, but if our line starts off with 5, 1, and then I add some scalar multiple of 3, 2, and the scalar multiple I can use t to represent any scalar multiple I want, then I would be able to draw out this whole line. And then now I've created this parameter t, which is that scalar multiple. Now I can call this, I don't know, L for line of t. So now it looks like a vector. If you're given 2 points, yeah. Okay. So let's take a look at the components here. We have our starting point, and we have our direction vector. And then we have t to be our parameter scalar thing. That would move you to a specific point and then scale the vector so that you can go to any point on the line. Okay?
It seems to be in the same formatting as y is equal to mx.
Not quite. It looks close, but it's not quite. That's a good observation, but it could be a little bit different. Yeah, it's not an x1, y1 kind of business. We can think about the direction as kind of like the slope, and then we can think about the starting point as a point in a direction, which, by the way, is going to be what we want. So define equation of line. We need a point and direction. Okay, so I tend to like to look at the drawing of this being animated as well. Now I know my drawing looks really cool, and it could be, you can almost see the animation here. But I think it actually might be better if you see it move. So let's find this equation of the line. Let's call it xy is equal to, and this is how we create vector functions in this particular program. So we got 5,1 for our point plus t times the vector, and the vector is minus 3, 2. So notice that this only draws a piece of the line. Actually, let's identify those points that we had. The point 5,1 and what is it, 2,3?
Oh, yeah. 2, 3, yeah.
So if we identify these points, 5,1 and 2,3, the line segment that was drawn only drew from those 2 points. It's not a whole line. Any ideas on what I'm doing here that's keeping it from drawing the whole thing? Because a line is, supposed to go infinitely long in either direction. You understand what I'm asking? Okay. Yeah, so for this particular program, when I draw a parametric equation or a vector function like this, it's going to assume that my t only go from 0 to 1. So if I extend this to, let's say, -1 to 2, that gets a little bit longer, right? No, I can't put infinite, but I could put something really large, like 99. Then, since my window is only there, suppose we can zoom out. All right. So, wait, this is not animating. Let's see. Did I promise an animation? Wait, what? Oh. Yeah, I think this is what I want. So I want to draw the vector, and the drawing is going to go from 0, 0 to some particular point. And I can't put t here because it's not going to graph it for me. Let me put 0 for now. And what I have is a vector that draws things out. it goes from 0 to whatever point that I'm pointing to. And if when t is equal to 0, I'm at that starting point, right? When t is equal to 1, I'm at the other point. So this is what I want to animate. When t is equal to 1/2, we're in the middle between those 2 points. When t is equal to 2, we're over here. When t is equal to -1, we're down here. So those are the points that we've identified in our drawing. And so now let's just make it equal to n, and let's let n go from, I don't know, -3 to 5. So now as my t changes, so I'm calling it n, as my n changes, and these are the numbers for n over here, which are the numbers for t, it's going to be drawing out that line. It's going to be putting points and points and infinitely many points until it draws a straight line. And if I stop at any time, -0.6, 1.4, 2.52. I'm a little bit further out of the screen, but that's the idea in drawing out this this graph. Okay?
And since the line's made of vectors, it has a direction?
Well, let's talk about that. Right now, we define this vector from 5, 1 to 2, 3, right? In fact, let's draw that vector. Can't see it. Maybe if I take the line out. So we define this vector from 5, 1 to 2, 3 to say that we're going in this particular direction. And so when we draw that line, we're going to start from whatever starting point we're starting, and then we're going to go off the positive and negative infinity and draw out that line. So it looks like it has a specific direction, but the question is, what if for some reason you forgot that the vector is head minus tail and then you did tail minus head? What do you think is going to happen? So it's not going to matter. It's going to change the direction that you're drawing this, but you're still going to draw the same line. If you do it wrong, then yeah, it could change things. In fact, we could change the starting point as well, right? Instead of starting at 5, 1, which is what we did, we can start at 2, 3, right? And change the direction, and we should still get the same line. Let's see if that'll work. So let's take a look at this equation that we got. We're going to continue to study this equation a little bit. And let's say this time we start at 2, 3. In the direction, and let's say we, instead of doing the subtraction, let's make it go the other way, or let's make it continue to go this way. -3, 2. Right? So this has the same direction as the line, whether you're going the same direction or the opposite direction. It's still going to be in the direction of the line. And this is a different point on the line. So let's call this L2 to differentiate from our first L. And then if we have a point and a direction, then the formula just becomes easy. It's just the point plus t times the direction. So clearly these two answers look very different, right? But would they draw out the same line? So I'm going to take my graphing calculator program and see if I can draw this. This graph, let's draw this in blue, I don't know. So we changed the initial point, 2, 3, plus t times 3, negative 2. Okay, let's graph it. Looks like it's drawing the same line, right? So in fact, it is drawing the same line, except it looks different. So we got two versions of the same line. Yeah, so the direction is important, and as long as you've got a point that's on the line, it doesn't matter which point it is, as long as it's on the line, you're going to draw out the same line. Okay? All right, let's dig a little bit deeper. And let's perform, I mean, these are vectors, right? And I think I kind of established earlier that if I have a point, I can treat it like a vector. So let me treat 5, 1 as if it was a vector. So this is like a vector addition, and this is a vector, a scalar multiplication. So I can rewrite my L of t as 5 minus 3t and 1 plus 2t. Did you understand how I got that? I did a couple of steps kind of quickly. I did a scalar multiplication on t, so I distributed the t to each component into this direction vector. And then I added 5 to the first component. I added 1 to the second component. You see how that happened? All right. So what do I have here? I have an x and a y value. X equals x minus 3t. Oops, let's call that 5 minus 3t. Y equals 1 plus 2t. Does that remind you of anything? These are parametric equations. So we just rewrote our vector equations into parametric equations. Right? I can do the same over here. Is that cool? So we went from the vector form to the parametric form. So now, I don't know if you remember when you guys were dealing with parametric equations back in Chapter 10, that they sometimes felt like it might be necessary to eliminate the parameter t so that you can write it just x and y without the parameter. So let's try to do that. Let's eliminate the parameter t. So I think this would be t is equal to x minus 5 divided by negative 3. Did I do that right? Subtract, divide. And then the next one, y minus 1 divided by 2. Subtract the 1, divide by 2. Hey, look, they're both equal to t. Well, if they're both equal to t, then they're equal to each other, right?
Yep.
Do you remember what law that was in algebra? One's equal to the other, and the other one's equal to the same thing, and so those must be equal to each other. What?
It's common sense.
It is common sense. It's also known as the transitive law. Transitive. Yeah, if A is equal to B and B is equal to C, then A must equal to C. Kind of follows.
Is that a lot in the, when you do the homework? If you have an issue with the problem, you get the solution, you'll see the two arrows.
Oh, yeah.
They'll have like three things, the arrows in between, so it knows that this one is that one, but they can also be in the middle. They do it a lot.
Yeah. So this, by the way, it's called symmetric form. There's something neat about symmetric form in 2 dimensions, though. This has an x and a y. So you should be able to make that into y equals mx plus b, right? Shall we? Get y by itself equals something x plus b. Well, why don't you guys tell me so I don't have to do it. I think you might need to do some cross multiplying. It would be negative 2/3 x. I'll go with a 2/3 x, negative 2/3 x, but 13/3. Can I get a verification on this? Negative? This is negative? Is it positive? Oh, so this would make this into a negative 5, positive 5/3, and you would add. I could, but you could. So 13/3? All right, can I just get an okay for this? Yeah. We'll go with it? Okay, thanks, Oscar. You guys got to practice your algebra. That's why you got to practice it. All right, let's write this other one into symmetric form. So we got this is equal to x, and this is equal to y. So if I solve for t for the first one, t is equal to x minus 2 divided by negative 3, and the y would equal to, the t here would equal to y minus 3 divided by positive 2. And if I set them to equal each other again in symmetric form, this is in symmetric form already, but if I carry on with the computation, what should this equal to? That's going to equal the same thing. I mean, do the work, and hopefully it does. So we do get the same line. Right? Okay. Is this negative? The 3? Yeah. Okay, cool. All right. So the neat thing about the symmetric form in 2 dimensions is that you can rewrite that and make it into your usual, the old y equals mx plus b business. All right, so let's go to 3D. And that's the power of doing these vectors and parametric forms of the line, is to be able to express these lines in 3 dimensions. And for starters, let's come up with a couple of points in 3 dimensions. Let's just jump into an example. Anybody want to throw out a couple of points? 3, 1, 4, and 6, 1, 9. No negatives? All right. If we follow the same process, we should be able to get the same results, right? So we have a point. We have 2 points, actually. We just need 1 point, but we also need a direction. So to find a direction, we need to subtract the 2 points. And I think we've already established that it doesn't really matter. In most cases, it doesn't matter. Sometimes it might matter which way you're going. But in most cases, it doesn't matter how we find our direction vector. So let's just do a subtraction. It doesn't matter which one. These numbers are higher, so I'll go 6 minus 3 is 3. Negative 1 minus 1 is negative 2. 9 minus 4 is positive 5. Okay. So I have my direction vector, and if I pick any of these points, I'll just say my line equation in vector form is going to be 3, 1, 4 plus t times the direction vector 3, negative 2, positive 5. Okay? And then I can in turn write this in parametric form. So just collect the x values. That would be 3 plus 3t. Collect the y values, 1 minus 2t. Collect the z values, 4. Except this one will have a z, right? The other example we did didn't have a z. 4 plus 5t. So now I have my parametric form. I have my vector form, parametric form. And then if we solve for t for all these and set them all equal to each other, then we'll get our symmetric form. So let's solve for all the t's. T is equal to, and you can kind of see the pattern here, right? X minus 3 divided by positive 3. That's for the x values. The y values, we got y minus 1 divided by negative 2. And the z value, we get t is equal to z minus 4 divided by 5. And so if we just get that information and set them all equal to each other, we got our symmetric form of the line. What might be a neat exercise is that if somebody gave you a symmetric form of the line, for you to be able to transform it back into a vector form, or parametric form for that matter. And then we can also view this with a graphing program that allows you to look at things in 3 dimensions. Let's take a look at it. Maybe I'll get a new one. So let's first get our points. Oops. 314. And 6, -1, 9. So here are a couple points we have in our space. Let's find that vector that we found, a direction vector, to make sure that it's going in the right direction. We went from head minus tail, so the head was 619, or 6 -19, so the tail was 314. So here we have the vector connecting those two. So now let's actually draw the line. According to what we got, we can write, this particular program allows you to write things in parametric form or in vector form. So we did our first example in vector form, so let's write the parametric form. And it's basically writing the x equation over here. So 3 plus 3t is what I'm seeing. And the y looks like it's 1 minus 2t. And the z looks like it's 4 plus 5t. So if we draw this line, this line is being drawn again from 0 to 1. So let's make it go from -1 to 2. A little bit longer. Make it thicker. So you see that it actually does go through those 2 points. And we use that vector to help us create it. That's a cool picture. Take a picture of it. All right, any questions? Guys got a good handle on these lines? All right, I think that was for the lines. Let's take a look at the planes now. 3 ways, find equations. So plane in 3 dimensions is what we're trying to find. And there's a lot of ways to try to describe a plane in 3 dimensions. One way to describe a plane in 3 dimensions is to have 2 points in space, and then every point that's equidistant from that point in space will make up a plane. Equidistant means the distance from that point to some other point is equidistant. It's the same distance. So if I have another point down here, as long as those distances are the same, I would get that value. So can you picture that eventually this will draw out a line if it's in 2 dimensions, and if it's in 3 dimensions, it would actually draw out a plane. Yeah? We need that VR club here, that we can see things in 3 dimensions.
I wonder if you could do it with the Google Cardboard, the phone app.
But you guys have to be able to visualize it too.
Yeah.
All right. So a line is or can be defined if you have a point in a direction. So it turns out that you can define a plane by a point and a normal vector. You guys know what I mean by normal? Yeah, so normalize is making it to unit length, but that's not what this normal means. So perpendicular orthogonal. We'll deal with tangent planes later.
Yeah.
A normal vector is a vector that's perpendicular to a plane. And if you have a plane, then it's pretty clear that the normal vector is going to be a direction that's perpendicular. And there's really, aside from going up or down, there's really just one normal vector. Not counting whether it's going up or down. I don't know. So let's say you have a point and a normal vector. What we want to do is be able to describe any point on this plane.
I'm having a little bit of trouble interpreting what I'm seeing. Is it like a flat surface and that vector is going upwards from it? Or
Yes.
Okay, so it's like a piece of paper with something sticking.
As a piece of paper, this is your piece of paper, and then
Pencil standing straight up.
and then this is perpendicular to that paper. So we have a point. We'll call the point, what should we call the point? Let's say x naught, y naught, z naught. Then we have a normal vector. What should we call this normal vector? Let's call it A, B, C. And then we have these random arbitrary points that are supposed to be on the plane. Arbitrary, random. So let's just call that some random points on a plane, x, y, z. I suppose if I want this to be points and vectors are the same thing anyways, right? So any random point that I choose here would be just considered x, y, z. It's arbitrary, it's random. So there was one special operation that we learned that had something to do with perpendicular vectors. With the cross product?
Yeah, it's cross product equal to 0, right?
The cross product of perpendicular vectors is equal to 0? This should be a clicker question. Yeah, out of time. The other product. What's a dot of two perpendicular vectors? 0. It's a dot product. So what I propose here is for us to make a vector from our random point to the given point. And what would that vector be? That vector would be just the difference between the two, right? So it would be x, y, z minus x naught, y naught, z naught. Now, regardless of what that x, y, z is, if that x, y, z is on the plane, then this whole vector is on the plane. Right? And if this vector is on the plane, then it has to be perpendicular to the normal vector. So n, turns out, is perpendicular to v, which means if we take the dot product of that, we should get equal to 0. So n is ABC. V, whoa, I have to subtract this. X minus x naught, y minus y naught, z minus z naught. And according to this formula, since these two vectors are perpendicular, we should get this thing to equal to 0. So this, well, let's dot it. Notice if you dot it, is it still a vector? Remember, the dot product gives you a scalar. So technically, this is a scalar equation. This is your equation of a plane, or at least one form of the equation of a plane. What I want to do next time is take a look at this equation, mess around with it, move things around, and we'll see that this is going to give us a quick way to find the equation of a plane. All right? Okay, that's it for today. See you guys tomorrow.